All right, class 9, good morning. We did up till here yesterday. Okay. Now from today we start from the laws of liquid pressure. Now remember one thing. I just want to give you a revision. Remember, pressure depends on the total pressure is atmospheric pressure plus the liquid pressure, and the liquid pressure is H rho. H is the depth, height, rho is the density of the liquid, and g is the acceleration due to gravity at that particular place. So these two factors are already there. Okay, height, that's the depth inside the liquid, that's one factor on which the pressure will depend, and the density of the liquid. Okay, right? And acceleration due to gravity, we don't talk about that, because at a particular place, whatever the liquid is, whether it is water or oil or whatever the liquid is, the acceleration due to gravity is constant. So basically it varies on these 2 points, the depth and the density, because g at a place is constant. So no matter what my liquid is, whether it's water or oil or any other form of liquid or mercury, the g remains constant. Now, the laws of liquid pressure. The first one, inside the liquid, pressure increases with depth. Now, that we already know. Fine. In a stationary liquid, the next one. Look at that. In a stationary liquid, pressure is the same at all points on a horizontal plane. Now, this is what actually they mean by this. So at a particular depth inside a liquid here, at a particular depth, throughout this horizontal plane, the pressure remains same here, wherever you go. Throughout that horizontal plane, the pressure remains same. The second point that we have, pressure is the same in all direction about a point in a liquid. The second one, pressure is the same here. Pressure is the same in all directions about a point in a liquid. Now actually they mean this here. Look at this particular one. Pressure at a point, at a certain depth. So at this point, the pressure is the same in all directions. This way, this way, this way, this way, this way, this way, this way. Now that doesn't happen in the case of solid, remember. That's why it's a point to be noted. In a solid, what happens? Whatever the pressure is here, if that is my solid block over there, solid, I apply the pressure here, the pressure is directly fell down, not over here. But that doesn't happen in the case of a liquid, remember. In the case of a liquid, at a particular point, the pressure is the same in all directions. Did you get that? Point number 3. Point number 3 says, right. Point number 3 says pressure is the same in all directions. That's okay. Point number 3. Point number 4, pressure at same depth is different in different liquids. Now that actually depends on the density here. So at a certain depth inside a liquid, if it is water, the pressure is different. If it is oil, the pressure is different, and so on. So at a certain depth, inside a liquid, the pressure is different for different liquids. Now that's actually pressure depending on density. We know that. That point there. Then comes the last one, liquid seeks its own level. Now because of gravity, the liquid always takes the lowest level on earth. Did you get that? Now we'll be seeing to that. Some consequences of liquid pressure. Pressure is HdG. Fine, look at some of them. In seawater, the pressure at a certain depth in seawater is more than that at the same depth in river water. Why? Because in seawater we have dissolved salts, so the density is more. Therefore, pressure at the same depth, say 10 meters. I take 10 meters inside the seawater and 10 meters inside river water. The pressure inside the seawater will be more. Why? Because the seawater has dissolved salts in it. The wall of a dam is made thicker. Look at that. We never find the wall of a dam like this. Okay, it's not a straight wall like that, not like the walls in your house or in the room. Okay, that's the wall over there and this is the water. No, what will happen, because the pressure over here will be more than the pressure here. Okay, so this wall will collapse from here. Okay, it will simply just give away from here. Okay, not here, it will just collapse from here. So what they do is they put a thing like that, so it is broader at the base and not so broad at the top. So it has more support over here. Why? Because the pressure increases with depth. Okay, so that's your dam wall. Then comes water supply tank is placed very high. Why? Because of this, the liquid seeks its own level. You've seen that people living in the flats, you see 10-story multi-story buildings. Okay, the tank is right on the top, but the person who's right nearest the tank gets the least water. Okay, or he might get the same water, but the person who's right down in the flat, okay, the lowest level, okay, he gets a better supply, he gets a better pressure of water. Why? Because liquid seeks its own level. Diver suit, okay, deep diving. You must have heard about that. Deep diving suits. When these divers, they go down, they wear a special suit. Okay, when they are going down 100 meters, 200 meters inside water, or might be 50. Why? Because the pressure increases with depth. If they go just like that, okay, the pressure of water will literally crush them. Okay, so they have a pressurized suit. The suit is pressurized from inside. So what happens when they go deep diving, okay, they are able to tolerate that pressure. Then size of a bubble inside the water. Look at that gas bubble here. Very nicely we do this na? Many a time when we are drawing an aquarium, you see kids drawing an aquarium, they draw a fish like that and they draw the bubbles. Look at that bubbles. Can you see? Starts from smaller, bigger, 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 bigger. It goes like this. Smaller, bigger, 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 and so on. That's how we draw a bubble. Unknowingly we do that. But there's a physics behind that. Reason is, as this bubble rises, this air bubble, as it rises up, okay, the pressure of the liquid reduces. So when the pressure reduces, the volume increases. You must have done that in Boyle's law. Okay, when the bubble is over here, the pressure is more, so the bubble is small. As the bubble goes up, slowly as the bubble is rising, the pressure keeps on reducing, so the volume keeps on increasing. Did you get that? Now, so much so about the laws of liquid pressure. Okay, there is a difference between laws of liquid pressure and laws and the pressure exerted by solids. Now we go on to transmission of pressure in Pascal's law. Now let's see what it has to say. It says, okay, let me go to the law straight away. Pascal's law states that pressure exerted anywhere in a confined liquid is transmitted equally and undiminished in all directions. Now again, as I said, there's a difference of pressure in liquids and pressure by solids. Look at that here. In the case of solid, if I apply a pressure, pressure is here only, not here. But in a liquid, if I apply pressure anywhere inside a liquid, the pressure is transmitted equally throughout the liquid. Now, how do they say that? Look at this. Suppose I tell you I have a container over here, right? And inside that there's a point X and there's a point Y. Okay, suppose I tell you the pressure over here is 10 and the pressure over here is 15. Depth is more, so the pressure will be more. Okay, what is the difference in pressure? 5. The difference in pressure is 5. Now when I apply pressure, some way or the other, if I increase the pressure here, if I increase the pressure there, okay, I cannot make this pressure 15 by not altering this pressure. I cannot make a pressure here and here the same. It can never be the same. Why? Because the depth is more. So if I apply pressure here and increase the pressure here, make this 15, this automatically becomes 20. Why? Because the pressure difference has to remain 5. Do you follow what I said? Okay, if I increase the pressure over here from 10 to 15, the pressure over here automatically increases from 15 to 20. So the pressure difference remains the same. it cannot happen that the pressure over here and the pressure over here is the same, even though the depth is different. Therefore, to maintain that pressure difference, the pressure over here also increases. Now, so what happens? Whatever pressure you exert over here, it is transmitted to this point also, equally. So if you increase the pressure here by 5, this pressure automatically gets increased by 5. That is Pascal's law. Okay, it is transmitted equally throughout the point, anywhere point. You can take one point over here, you can take one point over here. Okay, all these points, the pressure automatically increases to maintain that pressure difference. Did you get that? Now that is what we say is Pascal's law. Look at that. So Pascal's law states that the pressure exerted anywhere in a confined liquid is transmitted equally and undiminished in all directions throughout the liquid. Is that okay? Now we have a small experiment over there. So what they do is they say take a glass flask like this here. We take a round bottom glass flask here, and we have different tubes. Say one tube over here, one tube here, one tube here, one tube there. Okay, and we have a piston over there. Mind you, Pascal's law is applied to a confined mass. They say this is very, very important. This term is very, very important over here. A confined liquid, not to an open liquid. You go and apply pressure to the water that is flowing in the river. That's not Pascal's law. The water that is flowing in the river, you go and apply pressure over there and you say this is Pascal's law. No, it doesn't work like that. It has to be a confined liquid. That means a liquid that is in a container. You know the meaning of confined. Check it out. Okay, so it has to be inside a confined liquid container. So if it is applied to a confined container, what happens here? So when I apply this, push this piston down, the pressure comes down, and you find it's not that the pressure, there's a opening over here. It's not that you feel the pressure directly over there. No, you'll find from all the outlets the water is jutting out with the same pressure. From all the outlets, the water is jutting out with the same pressure. You just don't find them coming out just like that. Is that okay, all of you? Clear that much? Now that is Pascal's law. Now the application of Pascal's law in hydraulic machines. Now there are many types of hydraulic machine, but what is this exactly Pascal's law? How does it work? What is the mathematics behind Pascal's law being applied to a hydraulic machine? Now there are many types of hydraulic machine. Here, now look at this. This is the case over here. You take this here. All right, I think I need to go a bit deeper inside. Okay, let's understand this diagram. Okay, fine, look at that. So we have one container there with a piston A. This has an area, this piston has an area A1. We have other container over there with a piston B. This has an area A2. Now what I do is I apply a force over here F1. So when I apply a force over here F1, what is the pressure over here? P1. P1 is equal to F1 by A1, force by area. Okay, P1 is equal to F1 by A1. Now this P1, according to Pascal's law, travels throughout the liquid and it comes over here, P1. Okay, here I have a piston, okay, whose area is A2, and the force that is exerted over here due to this pressure is F2. So what is the pressure over here? P2. P2 is F2 by A2. Now according to Pascal's law, the pressure here and the pressure here is same. Therefore they put this thing. P1 is equal to P2. Did you get that? So if P1 is equal to P2, then F1A1 is equal to F2A2. Cross multiply, F2 by F1 is equal to A2 by A1. Now if A2 is greater than A1, as we see over here, if A2 is greater than A1, so for this ratio to be equal, F2 will be greater than F1. If A2 is greater than A1, then F2 will be greater than F1. Okay, So a small pressure over here, a small force here, F1, see F1, A2 is greater than A1, as you can see. So F2 will be greater than F1 for this ratio to be equal mathematically. Okay, so a small force here gets converted into a bigger force over here. Okay, so this thing acts as a force multiplier. Okay, this device acts as a force multiplier. Did you get that? And this device is used in many a thing. Okay, you don't have to worry about all these. Okay, right? It is used in, this is a hydraulic press. It's a Brahma press here. Then it works in hydraulic jacks over here. All right, are you getting it? This Brahma press is used to press cotton bales, big bales of cotton. They press it and they tie it up with the help of this hydraulic machine. They are all hydraulic machine and they all work under the same principle. Okay, right? They all work under the same principle. They are all hydraulic machines and all work under the same principle. You don't have to worry about the working part. Just remember, this is the mathematics behind it and you have small numericals on this. Okay, you can just go through the working of this. Got it, everybody? Okay, then you have the hydraulic press over here, which again works with the same principle. Okay, this is also a hydraulic machine, hydraulic jacks, okay, which is used in vehicles and all that as brakes. Okay, I think you have a hydraulic brake this side over here. There, you have the hydraulic brake over there. Okay, fluids. Okay, fluids are used as hydraulic brakes in your cars and buses and all that. Is that okay? Right, so you don't have to worry about the working of all these things. Just remember, they are all based on hydraulic. They are all hydraulic machines, but different uses have been put. Is it okay? Right, they don't ask you for the working of this. They don't ask you behind the principle is all hydraulic machine. The principle is Pascal's law. All of them, they work under Pascal's law. Is it okay? Right, now this we'll be talking more about this later on in class 10, where we have the mechanical advantage is load by effort. Okay, and you find that in the case of these hydraulic machines, the mechanical advantage is greater than 1. Okay, the velocity ratio, you won't understand this unless you do work power energy in class 10. Okay, this comes in class 10 as work power energy. Okay, velocity ratio is distance moved by the effort, distance moved by the load, that is also greater than 1, and so on, and therefore it is a force multiplier. Just go through this once. Okay, difficult to explain right now because this until unless you understand machines in class 10. Is it okay, all of you? Clear with that? Okay, right, we'll be going on to some numericals. Go through the exercise. Now start going through the exercise just now and see if you can answer these questions. Okay, okay, I'll be putting some numericals. Okay, how many numericals do we have over here? We have 14 of them. I'll try and do some of them. Okay, I'll try and do some alternative numericals. Okay, you do the rest. Okay, then the next class I'll do the rest. Okay, out of this 14 I'll be doing 7 of them. You try doing the others. Okay, as a practice, and the rest again next class I'll do the rest. Is that okay? That's it for today. Clear, all of you? Go through this exercise just now. Sit and go through the numericals done and try the numericals out and go through this exercise just now. Is it okay, everybody? Fine. Thank you so much. Okay.